In this video, I want to tell you more about latent state trade models. In a previous video, I introduced you to the idea of latent state trade analysis and latent state trade models developed by Rolf Steyer and colleagues, and I showed you this generic or very basic latent state trade model. So if you haven't seen that video on latent state trade models yet, then I suggest that you check this out first. In this video here, I want to elaborate a little bit more on latent state trade models, and I want to show you a model that actually is more appropriate for most empirical applications. In this model here, we have a single trade factor psi at the top, and we have state residual factors zeta at the bottom. The trade factor psi represents time unspecific effects or trade effects, so this is the factor that is consistent across time, whereas the zeta factors at the bottom represent situation effects and person by situation interactions. In addition, in the latent state trade model, we also have measurement error variables epsilon. So the goal of latent state trade models is that in longitudinal data where we have repeated measurements across time, we can then determine consistency and occasion specificity as proportions of variance that the latent factors explain in these manifest variables. Consistency is the proportion of variance that the trade factor psi explains. Occasion specificity is the proportion of variance that the state residual factors explain, and I explained that and showed that in detail in that previous video. Now, in this video here, I want to talk about the fact that this model here with a single trade often doesn't fit so well in empirical applications. In many cases, we apply a model like that to questionnaire data where the indicators YIT might be items or might be questionnaire subscales or item parcels or test halves or something like that. And typically in longitudinal data, we face the problem that we have indicator-specific effects or item-specific effects. Some people say those are method effects. And that means that the same indicator is often more highly correlated with itself across time than it is with the other indicators, due to there being stable item-specific effects that carry over across time. For example, when you measure subjective well-being and you ask people, are you happy? And you also might ask them, are you satisfied? Then the happy indicator might be more highly correlated across time with itself than with the are you satisfied indicator, because happiness and satisfaction are not exactly the same things, although they are highly correlated and are indicative of subjective well-being. But there is some specificity oftentimes in the items, and that leads to a correlation structure across time that cannot be well represented with a single factor, because the single factor psi here in this single trade multi-state model implies that we have unidimensionality of the trade effects, meaning the trade influences across time are assumed to be perfectly correlated across different indicators. And that's not realistic, because there might be trade components that differ between different indicators that are not perfectly unidimensional. Now, there are different ways that this can be addressed in longitudinal analyses. Oftentimes what people do in longitudinal models when they use multiple indicators, as here in this latent state trade model, is that they allow the measurement error variables epsilon to be correlated across time for the same indicator. And that's a possibility to account for those residual associations among indicators that are then not explained by the trade or the state residuals. However, it has certain disadvantages to allow error variables to be correlated. First of all, from a psychometric perspective, we would say, well, those error variables really should represent random measurement error. And so the fact that they are correlated then would indicate that they're not just representing random error, but also a systematic source of trade variance. And we don't want the systematic source of unique trade variance or indicator-specific trade variance to be confounded with measurement error, because then we would be underestimating the reliabilities of the indicators. We would also be underestimating the trade effects or consistency coefficients, because then a consistent source of variance is part of the error, and we don't want that to be part of the error. We want to separate it from measurement error. Also, when you allow for correlated errors across time, then the model becomes much less parsimonious because you have a lot more parameters to estimate, and then also many of those error correlations in practice are not significant. So meaning they're not significantly different from zero. And then what do? Do you drop these from the model? Do you keep them in the model? If you drop them, then the meaning of the trade factor might shift because then some indicators would not have indicator specificity. If you don't drop them, then you have a very highly parameterized model where you have parameters in the model that are not needed, you have an over parameterized model. So those correlated errors can cause a lot of different issues, and therefore I prefer to not have longitudinal models with correlated errors across time, whether it be latent state trade models or multiple indicator growth models or other kinds of multiple indicator longitudinal models. I prefer to use other approaches, and I want to show you one approach that specifically applies to latent state trade models that is very elegant to take indicator specific trade effects into account. Now, this model is called the latent state trade model with indicator-specific trades. We also sometimes call it a multi-trade, multi-state model, and you'll see why in a moment. This model was proposed by Michael Eid in 1996 and has since been applied very successfully in latent state trade studies in many applications. This model often fits very well. It's a very elegant way to account for indicator specificity without over parameterizing the model. It's a model that is not much more highly parameterized than a single trade model. So I want to show you how it works. You can see we have the same design here. We have 3 indicators again that were measured on 4 measurement occasions. And now in this model, rather than specifying a separate trade, a single overall trade for all indicators, we have indicator-specific trades. So we have separate trades for each of the 3 indicators. Xi1 would be the trade for indicator Y1t. Xi2 is the trade factor for indicator Y2t, and Xi3 is the trade factor for indicator Y3t. And so therefore, the indicator specificity is now captured by the trades, and we will properly separate consistency from measurement error and occasion specificity. We will not have an inflation of the error variance, and we will also not have an underestimation of the reliability of the indicators, because now this trade specificity is represented by separate trades. And this works very well because now you can also you can estimate the trade factor means and the trade factor variances separately for each trade. So the indicators could be measured on different scales. Previously, that was represented by the fact that indicators could have different intercepts and different loadings. In this case, now those trade factors can have their own means and variances, and therefore then the indicators could also be measured in different metrics. In this model, we have the same structure for the state residuals, so that nothing has changed there. We still have these time-specific residual factors that account for situation variance and person-by-situation interactions. In the model, the trade factors are allowed to be correlated, and those correlations tell us something about the homogeneity of the indicators. The more highly these trade factors are correlated, the more the indicators are homogeneous and are measuring the same trade. Or you could say the smaller the indicator specificity or the smaller the method effects, the higher those correlations. And for homogeneous indicators, you often find that these trade factor correlations are in the area around 0.9, and so then it shows that there's not much specificity. But there are also many applications where the indicators are more different and where those trade factors may only be correlated 0.5, 0.6, 0.7, and then this model allows for that. This model does not require those indicators to have unidimensional trade influences. And so it makes it very flexible when you model constructs that are maybe not so strongly related, where you have different facets of a more global trade, where the facets have higher specificity. Then you can still use this model to extract consistency and occasion specificity. And the coefficients of consistency and occasion specificity and reliability that I showed you in the previous video on latent state trade models, they work in the same way, except that now you have to use the indicator-specific trade variances, meaning each trade has its own variance, and so you have to take that into account when you use these formulas for computing consistency and occasion specificity and reliability, but otherwise this works in the same way. So you can see this is quite a simple and elegant way to account for indicator specificity when you use latent state trade models, and this model has been applied a lot, as I said, and those applications often show that the model fits the data well and that you can represent the structure, the longitudinal structure of constructs that have trade and state components quite well with this model. I hope you liked this presentation. Please check out the videos that I also offer on this channel. Subscribe to this channel and look at the description for more workshops on statistical methods, and leave a comment in the comment section if you want to have other topics covered here, and I'll see you next time.